There are numerous ways to differentiate fat tissue by location and by function. And it's the latter that we're addressing at this point, where we're talking about the functional differences between fat storage depots. And as you noted, we call one of these depots white adipose tissue, and the other we can call brown adipose tissue. It is, in fact, because of a difference in color. One of the things we do in my lab is do fat biopsies from humans from around their belly. And we'll take out a little piece of fat from the belly, and it is very whitish, a little yellowish. And it's because it is primarily just fat. In a fat cell, it is almost entirely made up of a big drop of fat, like a bubble of fat. And it looks a little bit like Crisco almost, not quite as pristine, or like coconut oil. Maybe I'll put it that way. So that is white fat. And it's white, again, because of the incredible amount of fat. You can't see that is in those fat cells, and you can't really see anything else about the cells. In contrast, brown adipose tissue has small drops of fat within its cell, but it also has a very high preponderance of mitochondria. In mitochondria, the so-called powerhouse of the cell that everyone remembers from biology, from high school biology, the mitochondria are in fact a reddish, kind of brownish, darkly complected color. And the fat tissue that is so enriched with those mitochondria reflects that tissue. I mean, it literally reflects the light, I should say. And so it looks much more kind of reddish brown. And that not only do we see that stark difference in appearance, I mean, it actually looks more in color like muscle in color than it does other fat tissue. But with that difference in appearance is a profound difference in metabolism. And this kind of reflects the fact that white adipose tissue does indeed store fat very well. It's no surprise that white fat cells have a very low metabolic rate. Of all the cell types we've tested in my lab measuring metabolic rate in tissues, fat has by far the lowest. And then when we measure the metabolic rate of the brown adipose tissue cells, they are about 10 times higher. Its metabolic rate's about 10 times higher. In fact, it's in the same range as muscle cells. And so that's a pretty substantial effect. Now, the difference goes even one step further, that not only do the brown adipocytes have a much higher metabolic rate, but then the question is, what for? And that might sound a little academic of a question. What for? What is the metabolic rate for? By that, I simply mean, what is the cell burning that energy for? Because a cell will normally burn energy based on what the cell needs. And for example, muscle and even fat tissue, basically the muscle or the fat cell will say to the mitochondria, hey, mitochondria, the cell, all of the cell, we need this much energy to do our job. Now, as I noted, muscle tissue has a much higher metabolic rate than white fat cells do. That's just because they're doing so much more. But regardless, the cell will tell the mitochondria, we need to do this much work. So give us this much energy. And that process is very coupled. That's what we call it. It's a very tightly coupled process. An analogy for this would be like someone who's driving a stick shift car and they're revving the gas and they see the RPMs driving up, really revving up, but they're keeping their other foot on the clutch, or the car isn't in gear. And so the speedometer, the actual amount of movement in the car, is nothing. It's not matched. So the RPMs are revving, but the speed isn't moving at all. That's uncoupled. That's when we've teased the two processes apart. So the instance I was just talking about, we're revving the gas and we're moving at the same time. The car is in gear and it's going down the road. Now, as I mentioned, in the uncoupled state, which is what we have with the mitochondria in the brown tissue, that's basically when the cell isn't demanding work from the mitochondria. The mitochondria just keep burning energy. So we're revving the engine, but not because the cell needs any work done. It does, but its needs are adequately met. In this case, the mitochondria in the brown fat cells are uncoupled, as we say. And in this case, they are just burning nutrients. They're burning fat. They're burning glucose for no cellular work that the cell needs done. It's just to create heat. And heat is a chemical like waste. biochemical waste. It is sort of the sign of a wasting of energy, back into the universe, if you will, or into the atmosphere. But in the human body, that does serve a purpose, particularly when we're babies. A newborn baby has a relatively high amount of brown fat. So of amidst all the chub on the baby is a relatively high amount of brown fat. And this is good because the newborn baby doesn't have enough muscle to shiver very well. And so it stays warm. If you lift your adorable little baby out of the bathtub, and he or she is going to stay warm, not by shivering, but by having all of this brown fat that suddenly turns on and starts chewing through nutrients just to create heat. Now, as we grow and our muscles grow and our body changes substantially, the relative amount of brown fat we have drops precipitously. And then much of the fat we continue to gain throughout our life is white fat. And that's okay, it works, because if we're cold, we can shiver. However, we know that adult humans who have more brown fat or whose brown fat is more active, and we can talk about that, they are much more resistant to diet-induced weight gain and diabetes and other cardiometabolic complications. Now, on the human body, the white fat is basically the fat that you can pinch and jiggle. That's all of our subcutaneous fat, and a little bit of fat within the abdominal space called visceral fat. And then humans have designed little pockets of brown fat kind of sprinkled throughout the thoracic cavity and up into the neck. Now that's not a lot, but my lab has found that when the white fat cells start consuming ketones as an energy source, they will actually enhance their mitochondria number, and the mitochondria will be more uncoupled. So we found in humans that when humans were in ketosis, their fat cell metabolic rate went up by 3 times. Now, that didn't get up to the 10 times higher that you see with brown fat, but still a tripling of the metabolic rate of fat cells is nothing to sneeze at. And this might be why
of the white, sorry to interrupt you, but of the white adipose tissue. So
that's right. That's exactly right.
Okay.
Yeah. So that's a process that is referred to as beiging. So it's like the white fat cell hasn't fully become a brown fat cell. It hasn't, and it can't, but it started to act a little bit like those brown fat cells. So it's not quite brown, but it's not quite white anymore. It's beige. And so we say that it was a beiging effect. So we found that the ketones have a beiging effect on the white fat, increasing their mitochondrial content and making the mitochondria behave in a more uncoupled state. Now, it's no surprise to people to learn that cold immersion will do the same thing, but that's, of course, a much less pleasant phenomenon by many standards than just being in ketosis through fasting or dietary control. But nevertheless, it does touch on the fact that you can leverage this biochemical phenomenon to have your fat cells start to really work in your favor in order to facilitate weight loss. So ironically, the fat cell begins eating its own fat as its metabolic rate has climbed, further facilitating fat loss. So that's really the maybe deeper than I intended to get, the differences between white fat and brown fat. They're very substantial differences, and we can kind of take advantage of that through lifestyle intervention.
No, that's perfect. That's even more like all the detail, all the nerds that are listening to this all are just like frothing at the mouth right now. So that's great. Yeah. Good.